Hello everyone. Today we will talk about torque. What is torque? Torque is, in the simplest terms possible, it is just a twisting force that causes a rotational motion. It is the rotational equivalent of the linear force. Just like a linear force can be thought of as a push or a pull, torque can be thought of as a twist. Mathematically, torque is represented as the vector cross product of the position vector and the force vector, where the position vector is the distance between the pivot point to the point where the force is applied. In the scalar notation, torque is defined as the product of three terms. One is the force, the second one is the distance, and the third one is the angle is the sign of the angle between the first two. If R and F are perpendicular to each other, that means the angle theta, it's 90 degrees. In that case, that distance R is called the line of action. It's a vector, that's why it's a line. In the diagram you see to your right, you have a force which is applied perpendicularly to the lever, and that force, if it's multiplied by the distance from the lever's fulcrum, you get the torque. So a force of 3 newtons, if it's applied perpendicularly 2 meters from the fulcrum, it will exert the same torque as the force if the force is 1 newtons and if it's applied perpendicularly 6 meters away from the fulcrum. So before we look at some examples of torque, let's look at what center of mass is. So center of mass is that point where the whole mass of the object can be thought to be concentrated. It's the point where the object is balanced. Mathematically, it is the point where all the internal torques cancel each other out and the sum of those torques is 0. For example, the beam that you will see in your experiment has a center of mass which lies exactly at the center of its length. The center of mass may or may not lie inside the object itself. For example, you take a ring, the center of mass of that ring is at the center of the ring itself, not inside the ring. So let's take up an example of torque. Let's say there is a person who opens up a door. He applies some force at the doorknob and opens it. Over here, the torque is applied at you have different positions where you can apply that force. Case A, if you apply that force at the hinge of the door, you do not get any torque. Why is that? Because the distance R in that case is 0. Because the force is applied at the pivot point itself. You do not get any rotation. Case B, if you apply the force at the other end of the door, you get a lot of torque. Why? Because you are at the maximum distance possible, so your R is as high as it can be, and the force, let's say if you keep the force the same, you get the maximum torque. Case C, if you apply the force in the middle of the first two, you get half as much as torque. Case D, you are applying the force at the same distance, and as you can clearly see, the force is applied is the same. But in this case, you do not get any torque because the angle between R and F in this case is 0. But in the previous cases, A, B and C, that angle was always 90 degrees. So the sine of 90 is not 0, but the sine of 0 is 0. So again, you do not get any torque. So this is the reason why the doorknobs are at the opposite end of the hinges. So now you know what torque is and how you calculate it. Let's see how you balance them if you have more than one torques acting in a system. As you can see on the figure on your right, you have two equal masses, but they are at unequal distances from the pivot point. But the force would be the same because the weights are the same. So the torque in this case will depend only on the distance from the pivot point. Whichever mass is at a larger distance will create a larger torque. So the one that lies at 50 centimeter from the pivot point creates a larger torque than the one which is at 30 centimeters. The mass on the right of the pivot point creates a torque in the clockwise direction, but the mass on the left creates a torque in the counterclockwise direction. So the plank rotates in the clockwise direction because the mass on the right has a larger torque. Let's take another example. As you see in the bottom of this slide, you have two people which are exerting the same force, and in this case they are at the same distance from the pivot point. In this case, both of these torques will be the same, of course in opposite directions. In this case, the seesaw would be balanced because the torque is the same, they cancel each other out. Let's see how you do this mathematically. The person on the left hand side of the pivot point is exerting a force of 50 newtons and he is sitting at a distance of 10 feet from the pivot point. So the torque in this case is Rf. Over here the angle theta, it's 90 degrees and sine of 90 is 1. So you just take the product of the distance and the force. So you get a torque of 500 Newton foot in the counterclockwise direction. And the person on the right will create a torque which has the same magnitude, that is 500 Newton feet, but it would be in the clockwise direction now. So when you add them, you try to get the net torque. It becomes 500 Newton feet in the counterclockwise. You add to that 500 Newton feet in the clockwise direction. But 500 Newton feet in the clockwise direction is the same as negative 500 Newton feet in the counterclockwise. So when you add them, you get 0. So the seesaw remains balanced. Let's look at Newton's second law now. Before I go ahead and talk much about torque and its comparison with the linear force, let's look at the angular momentum as well. So much like torque, the angular momentum is the cross product of the position vector and the linear momentum. From your previous labs, you know what force is. How do you get the expression of force? It is the time derivative of linear momentum, or the rate of change of linear momentum with time. So when you plug that value of force in your expression of torque, you get torque as the time derivative of the angular momentum, as you see in this formula, or the rate of change of angular momentum with time. According to Newton's second law, as you have studied before, if there is no net external force acting on your system, the linear momentum remains constant. It does not change. Similarly, in rotational mechanics, if you do not have any external torque acting on your system, in that case, the angular momentum remains constant. The expression of torque, the time derivative, or the change of angular momentum with time, if it's 0, that means the angular momentum does not change, or it remains constant. That's Newton's second law in rotational mechanics. So let's look at some analogies that you have seen in the lab of rotational mechanics before. You have seen that displacement is equal to the angular displacement in rotational motion. You have seen all of this before, so I'll just skip directly between the analogy of force and torque. Force, the general expression of force is mass times the acceleration. The counterpart, or the rotational counterpart of acceleration, is angular acceleration, and the rotational counterpart of mass, as you have studied before, it's moment of inertia, or how that mass is distributed inside a body. So when you take those rotational counterparts and you take the product of them, you get torque. That is another expression of torque. So tau is equals to moment of inertia times the angular acceleration. I hope this is all that you will need to know for your lab of torque. Thank you.